Good afternoon. My name is Thomas Recknagel. I work for the Global Runoff Data Center GRDC. In May 22, I gave a hands-on introduction to using R as part of the Eurofriend workshop series. Since the recording was lost due to a defective hard drive, I have recorded the main steps again. I hope it will be useful to some of you. Brief overview of the workshop. First, we'll open RStudio as well as the project on my binder. Then I'll briefly motivate why using R is in the spirit of reproducible science. After that, I'll give a short introduction to the RStudio IDE. And finally, we'll work through 7 examples together that should serve as a basis for you to further explore R on your own. So, before we start, please go to the website mybinder.org. There you enter the GitHub repository wmo-grdc/IAHS_workshop and then you click on launch. Okay, let's do this quickly together. This is the website mybinder.org. We enter the GRDC GitHub repository, which is wmo-grdc, and then /IAHS_workshop. wmo-grdc/IAHS_workshop, and then you click on launch. It may take a while to start up, but you should eventually see this screen. You can now click on the RStudio button to start RStudio. You might have come across the term replicability crisis or also reproducibility crisis. In general, that means that often it is not possible to reproduce the results of scientific publication. The use of the terms replicability and reproducibility is inconsistent. However, reproducibility is usually understood to mean that data and software codes are available in their entirety in order to obtain the same results from the same initial data. Replicability, on the other hand, is commonly understood to mean that different researchers, each using their own data and analysis methods, obtain the same results. In hydrology, a lack of replicability may also play a role. However, our focus here is on reproducibility. To get started, I recommend 2 papers. One by Christopher Hutton, Thorsten Wagner et al., a 2016 commentary published in Water Resources Research with the heretical title "Most Computational Hydrology is Not Reproducible, so is it really science?" And second, a study by James Steggy, David Rosenberg et al., published in 2019, assessing data availability and research reproducibility in hydrology and water resources. The latter examined 360 of nearly 2,000 articles published in 6 journals in the field of hydrology and water resources in 2017. One finding is that less than 7% of the results were reproducible. In recent years, the issue of reproducibility in hydrology has come under increased focus, and there are a number of initiatives and approaches to improve the situation. Another article I like to refer to in this context was published in Hydrology and Earth System Sciences in 2019, Using R in Hydrology, a review of recent developments and future directions. It explains very nicely how the consistent use of scripting languages can replace non-reproducible steps. There is a nice figure in the aforementioned publication showing the steps of a reproducible workflow from raw data to publication and indicating corresponding R packages. The goal of this workshop is not to give a structured introduction to programming with R. but I want to make it easier for you to get started by showing small concrete examples that you can try out directly and that will serve as a starting point to explore the world of R yourself. We now see the RStudio user interface. The first thing we'll do is we open the example number 1. To do this, we go to the file system at the bottom left. In the examples folder here we click on the file example1.r. Another sub-window will now open with the source code of the script. So our user interface is now divided into 4 sections. Let's take a closer look at them now. At the top left we find the source code of our script. If we'd open more files, we could access them via the different tabs. On the bottom left we have an R console where we can enter R commands directly. Can demonstrate this. Let's assign value 1 to a variable a, and we'd also have access to a terminal console here. In the upper right window, the environment and history tabs are of particular interest. In the former we find the variables and functions present in the current R session. So now here we see the variable I just created, a with the value 1. Under history we find a history of the R commands that have been executed. We have just used the access to the file system in the lower right window. We'll get to know the plots tab here in a moment. Under packages we find the installed R packages, and here we could also load and unload them. In example 1, I would like to introduce you to a package developed by my colleague Bastian Klein from the German Federal Institute for Hydrology. This package is called hydts, and it's used to work with hydrological and meteorological time series. It is not yet on CRAN, which is the R package repository, but it can be downloaded from our FTP server. The link you can read here. In our MyBinder project, the package is already installed. So now let's go together through the script example1.r. We will run each line of code by either pressing the Run button in the top bar of the sub-window here, or by pressing Ctrl Return on our keyboard. In the first line we load the package hydts into the environment so we can access the functions of this package. The package contains some example datasets. With the next statement we load some temperature data from German Weather Service. We can now access this data using the object dwd_tmean. Since this object stores a time series, it obviously is not a scalar variable. But what type of object are we dealing with here? The command str, like structure, helps us. Increase the size here a little bit, and now we can see that we have an instance of the hydts reg class here. That reg stands for regular. So this class is defined in the hydts package and is used to store time series with equidistant time steps. The show methods command lists the methods defined for this class. Let's try some of these methods. With the command values we can access the stored numerical values, so we will get a data frame with a column for each station. The command getTimeStep returns the length of the time steps. In our example it is 1 day. With meta, we get a data frame of the metadata stored in the object. And a simple plot we can create using the plot command. With the dollar operator, we select the desired station. And now we see that the plot appears in the lower right window in the tab Plots. In the next step, we want to calculate annual averages from the daily values. We use the aggregate function for this purpose. In addition to specifying our time series object as the first parameter, the function requires two more parameters. The parameter by expects a vector of grouping elements as long as the number of time steps. So each value is mapped to a group name. The parameter fun specifies the name of the function with which the summary statistics are to be calculated. To generate the vector of grouping elements, the hydts package provides several functions. For now, we use getYear to assign to each value the calendar year to which it belongs. So this vector is now stored in the variable years. And you see this is just one entry, the number of the year mapping to the values of the time series. So using this variable as the second parameter for a function call aggregate, and using the standard function mean as the function which should calculate our statistics, we will get our result, a data frame with two columns. First column holding the respective years, and the second column the calculated average values. Since no values were available for the years 1870 to 1900 for this station, NA values are included in the result here. To remove these values from the resulting data frame, we select a subset by using square brackets and the corresponding indices. If we look at the structure of the data frame, we will also see that the object type of the column group 1, which holds the names of the years, is of data type character. Therefore, in order to plot the series and add a trend line later, we need to convert this column to the numeric type. We will do this with the command as numeric. Now we can plot the time series again with the plot command. We'll add respective axis labels with the xlab and ylab parameters. With the last command sequence, we add to the plot a linear trend line. For details about the used commands lm for linear model and abline, I refer to the help system. In the second example, I'd like to show you how to download discharge data from the GRDC data portal and how to process and display it using the hydts package you just learned about. The GRDC data portal can be found at the web address portal.grdc.bafg.de. Use of the data is permitted for non-commercial purposes only. Before downloading, you must agree to the data policy, which contains further details on the terms of use. As an example, we want to download discharge data from the Kinshasa station on the Congo River. In the menu item Download by Station, we can either search for the station directly on the left or find the station by zooming in on the map. To select the station, we use the Recknagel tool in the upper left corner. After selecting, the data can be downloaded using the link that appears below. For this purpose, contact details and information on data usage must be provided. In our example project, the time series is already included. You can find it as a text file in the examples folder. Now let's look at the script example2.r. We load the hydts package again. For reading, we use the standard function read.csv. As we see in the text file, the data is separated with semicolons. And since the data starts in line 37 and they are column headers, we specify 3 parameters here in our function besides the file name. Header is set to true. The separation character is semicolon, and skip is set to 36. This means that the first 36 lines are ignored. We have stored the data in an object called congo.data. Let's have a look at the structure of this object. We see a data frame with 3 columns extracted from the text file. To be able to use the functions of the hydts package, we create an object of the hydtsRec class from the data frame. So this requires 2 parameters, the timestamps and the actual data. The timestamps must be POSIX-T objects. We can easily convert the date column with the s.posixct command. Since the column with the discharge values is already present in our data frame as a numeric vector, no conversion is needed here. We can simply specify the column as the data parameter. We now specify the station name with the statnames command. A simple plot can again be created with the plot command. In example 1, I showed you how to aggregate a time series with daily values to mean annual values. Analogously, we now create a time series with average monthly and annual values and plot them. Now let's move on to the third example. We open the file example3.r. In this example I want to show you how we can test our time series for trends. It's necessary to have run example 2 before, so that the objects with the time series are present in memory. Included in the R package trend are several statistical trend test procedures, including the Petit test for breakpoints and the Mann-Kendall test for monotonic trends. We see in the command reference of the Petit test function that either a vector of class numeric or a time series object of class TS is required as an argument to the function call. Since our time series object is of class hydts, we need to convert it. We could either get a vector of numeric values with the values command, as it is done here. However, we could also use the s.ts command from the hydts package to get an object of class ts. That would look as follows. Add the hydts object as an argument, and here you would see the converted ts time series object. But for now we just use the numerical vector as argument for the function call. So yeah, we can call now the petit test function, and here we see the results in the lower left window, and we see that in this time series the petit test does not find any significant breakpoint as the p-value is 0.11. The next function call I want to demonstrate is the Recknagel test for monotonic trend. And also the Recknagel test of this time series does not show any significant trend. However, if we take a subset, in this case I take the time series from 1962 to 2002, which would be the index 60 to 100, we would find a significant trend for this period, as p-value here is 0.0027. As I mentioned earlier, I only want to demonstrate here how these functions are applied in the code. So for details about the statistical tests, like definitions and assumptions and so on, I refer to the relevant literature. The next example is also very short and shall demonstrate how easy it is to display spatial geodata with R. Besides run-of time series, you can download shapefiles with the boundaries of the respective catchments from the GRDC portal. In our project, the polygon of the catchment area of the Kinshasa station is already stored. The file is called stationbasins.geojson. We load the library sf and use the function sd_read to read it. A simple plot can again be generated with the plot command. Very easily, however, we can also embed the polygon in an interactive map. The leaflet package is an interface to the popular JavaScript library Leaflet. With this simple sequence of instructions, we create a leaflet map with the standard OpenStreetMap layer and the catchment of area of Kinshasa station superimposed. Now I will show you some basics about working with raster data. In the project there is an example file in netcdf format. It's here example.nc4. It's modeled runoff data from the global hydrologic model WaterGap. Since the netcdf file contains multiple layers, we use the stack function from the raster package to read in all layers as a raster stack. When aggregating the original monthly values to yearly values, the layers got somehow strange names, so we use the names command to set the layer names to the corresponding years 1901 to 2016. With the dollar operator we can extract a single layer from the stack now. A simple plot is again done with the plot command. For a logarithmic plot, we run the log function on the extracted values and overwrite the grid with them. If we plot it again, we see that now we can the structures can be seen better now. We can add the catchment boundaries from the previous example to the plot. For this we set the parameter add to true. With the crop command we can crop the raster to the bounding box of the catchment. And again we can plot the cropped part of the raster together with the catchment boundary. In the next example we want to extract a time series from the raster object, namely the time series of the mean annual discharge values of the raster cell in which the station Kinshasa is located. Using the approximate coordinates of the station, we can determine the cell number using the cell from xy function. With this cell number we can directly extract a vector with the values. In analogy to the previous examples, we again create a hydts object that stores the time series. We can now plot this time series with the model-based data. To add the aggregated time series of the measured values from the previous examples to the plot, we use the lines command. It's more convenient to merge both time series into one hydts object. This can be done with the command merge. Now the time series can be plotted with one command. We get a JavaScript-based interactive plot with a digraph command from the digraphs package. Finally, I'd like to introduce the hydroGOF package. This package contains common goodness of fit functions that can be used to compare simulated and observed hydrological time series in particular. Again, I point out that this example is only intended to demonstrate how the package can be used from a technical point of view. For the theory of the included functions, please refer to the relevant literature on statistical methods in hydrology. With the function KGE, the Klingupta efficiency can be calculated. As parameters sim and ops, we pass respectively our time series, which we convert before, as already mentioned, as a TS object. As return value we get the Klingupta efficiency. You see here in the lower left window. Finally, I'd like to show you how the sapply command can be used to calculate statistics over a rolling 30-year window. Here we specify as the first parameter a sequence of starting years, in our example from 1903 to 1986. And the second parameter is a function that calculates the Klingupta efficiency for a section of the time series in each case. We can plot the result again. Of course, this also works with another goodness of fit measure, for example with the Nash-Sutcliffe efficiency.